Now the next topic that we are going to discuss in the context of this Bernoulli's equation is the use of such equations. See, the Bernoulli's equation has been one of the very popular equations in fluid mechanics, not just because of its simplicity, but because of its applicability in an approximate sense in terms of quantifying the nature of or the principle of working of many engineering devices, and we will look into such examples of applications of Bernoulli's equations. So some of the examples we will not detail very much, but we will only get the essence. The details of most of these examples are uploaded in the course website through a note on the applications of the Bernoulli's equation. So if you go through that in details, you will get all the detailed picture, because we are going to discuss subsequently about certain devices. These devices have certain intricacies and we will only highlight the major or the important features, but for the other detailed features you should refer to those notes. Now before coming to any device of very great engineering application, we may come up with a sort of a very primitive device which you have already heard of, something called as a siphon. So if you have say water in a tank like this and you are having a bent tube which is sort of sucking water and ejecting water to a different place from the tank. So this is called as a siphon. The apparent amazing feature of the siphon is, out of nothing it is pulling the water in the upward direction. That is the apparent amazing feature, but if you look into it a bit carefully, it is not at all any amazing feature, because eventually when it is discharged at a level below. So the actual head difference which is working on it is this one, which is a favorable one, because effectively it is coming from this elevation to this elevation, and this net elevation difference is actually giving it a velocity. So with that velocity the water is being sucked. So the fact that it is going up is nothing very special, because eventually it comes down and it gets ejected from a height which is less than or below the level of the tank, okay. But the good thing is that while doing it, it can traverse a vertically upward distance. Question is how much distance it can vertically traverse. So what should be this, say if we call this as h, then what is this h max? This is given by a practical consideration. Let us try to identify a streamline which connects the points, say the streamlines will be bent like this, but let us just consider a streamline which is confined between that points 1 and 2, which are almost like a located on a vertical line. So if we are interested to write the Bernoulli's equation, we can write P1 by rho plus V1 square by 2. So every time whenever we are writing the Bernoulli's equation, we are not repeating the assumptions, but you should keep in mind that what are the assumptions on the basis of which we are writing it. So P1 by rho plus V1 square by 2 plus GZ1 is equal to P2 by rho plus V2 square by 2 plus GZ2. Now you can clearly see that at the level 1 you have pressure as the atmospheric pressure. So this is P atmospheric. V1 is approximately equal to 0, just like the Torricelli's equation, because the area here is so large that the velocity with respect to which this level is changing is very small as compared to the velocity here. V2 is same as the velocity at which the jet is ejected here, if the area of cross section remains the same. So V1 is small because A1 is large as compared to the area available at 2. Then V2 is equal to Vj, that is the velocity at which the jet is coming out if the cross section is same, and you can find it out that Vj is nothing but approximately root 2 g into this capital H by writing the Bernoulli's equation between 2 points on the same streamline, whether if you continue with that streamline it goes like that and comes out. So the net elevation difference will remain this one if you write the Bernoulli's equation along a streamline between say points 1 and say a point j which is located here. Now when you write that one, what you will get? You will get P2 by rho is equal to G into Z1 minus Z2. So G into Z1 minus Z2 is minus GH minus Vj square by 2. Okay. So you can clearly see that if you take the atmospheric pressure as 0 reference, so this is written by taking atmospheric pressure as 0 reference. So this is like a gauge pressure. So when you take the atmospheric pressure as 0 reference, then P2 is negative because H is positive, Vj square is positive. That means the pressure at this point is below atmospheric. So if it is below atmospheric, it may come to a state when it comes to the vapor pressure, local vapor pressure. So when the pressure falls below the local vapor pressure, then what happens? Then vapor bubbles are formed. So when the vapor bubbles are formed, it's nothing very special that vapor bubbles are formed, but what is special is that when these vapor bubbles are transported or moved to a different place where the pressure is again higher, they will collapse again to form a liquid, and once they collapse, what happens? Basically then they were occupying a large volume, but when they collapse again to be converted to liquid, again there is a volume change. So it creates an unsteadiness in the flow and it can create a lot of vibration and noise, and that is not so good for the flow, and that type of phenomenon is known as cavitation. We will see in details what is cavitation when we will be discussing about the fluid machinery, which will be our last chapter in this particular course. So we will not go into the details of like what is cavitation at this stage, but we have to keep in mind that it is better if we keep the pressure at 2 below the local vapor pressure, that is below the vapor pressure which should be there at that corresponding temperature, so that vapor is not formed. So that means we are keeping a restriction that P2 must be less than the vapor pressure at that local temperature of the fluid. So then you can see that you get one H max from that, and that is the maximum H with respect to which you should design your system, so that you do not have a problem with formation of vapor. So the siphon in principle may be designed to be very like tall in height in terms of this bend tube, but in practice one should not make it too tall, because if you make it too tall, it is possible that the pressure is so low that vapors are formed, and that can create other disadvantages in terms of operation of the device. Okay. The next application when we will consider, we will keep in mind that now whatever applications we are going to study, our objective will be to have the Bernoulli's equation utilized in devices through which we are interested to measure the velocity or the flow rate in a say pipeline. So let us take an example. Let us say that you have a pipe like this, a horizontal pipe. Now water is flowing and you make certain holes in the pipeline. What holes you make? So first you make a hole like this. So when you make such a hole, what will happen? The water will rise and it will come to a height. Okay. The height with respect to which the water rises will be an indicator of the local pressure at that location. Pressure at where? See, we are interested about the center line. So if we are interested about a point in the center line, what we are doing, we are sacrificing one thing, we are not able to exactly probe at the center line. At the same axial location we are probing at a point which is different from the center line, and we know that it is very much possible that the pressure at the center line should be different in general from pressure at this. When they are different? When you have a curvature of the streamline. We have just in the previous lecture seen that if you have the gradient of pressure in the direction of n, you have only when the streamlines have a radius of curvature which is non-infinity. But here if we consider that the streamlines are parallel to each other, then you do not have that effect of the streamline curvature in terms of the pressure gradient. So whatever is the pressure here should be the same as the pressure here. So then this is an indicator of the local pressure. Now say we are interested to have an indication of the velocity. So for that what we can do, we can have another tube where we make a penetration in the wall, but before that we have the tube directly confronting with the flow. So this tube and this tube is different, this is not directly interfering with the flow, but this is directly interfering with the flow. When it is directly interfering with the flow, it is bringing the flow to a standstill or a dead stop. So it is creating like a stagnation point where the flow comes to a dead stop, it cannot go further. So whatever water was coming here, it comes to a dead stop, what it will do, it will enter, it will rise through the tube, and the question is, will the rise will be greater than this one or less than this one? See, this rise was the function of the pressure. Now what, so the entire energy which was there in the flow, if we assume that assumptions of the Bernoulli's equation those are valid, now we have made the kinetic energy to 0. So the entire energy, now contribution of pressure term plus the kinetic energy term will be successful to make it go further up, because that where will that energy go? You have made the fluid to a dead stop, you are assuming that it is a frictionless flow, then where will that energy go? It will obviously make the fluid rise to a greater height, and the difference between these two heights is, if these points are very close to each other, the pressures are almost the same, the difference between these two heights is just v square by 2g. So from this principle, v is the velocity of flow at this point. So from this principle it is possible to make an estimation of the velocity, and if you know the estimation of the velocity and if you assume it to be uniform, then you can also have an estimate of the flow rate. Now if it is not uniform, you can keep it at different radial locations and you can even find out how velocity varies radially, because this tube you can put at different radial locations. So this is put at r equal to 0 at the center line, but you can also keep it away from the center line. So at different radius if you put, it will give you a picture of velocity at different radius. So it is possible even to get a velocity profile if this is quite accurate. Of course there are many doubts about the accuracy of such a simple arrangement, but it gives us a conceptual understanding. So the device which is based on this conceptual understanding is known as a pitot tube. So the last T is silent, so it is pronounced as pitot tube. Okay. So this of course is to honor the name of the inventor of this device, and it is a very simple device, and the working principle of this device is based on two important definitions which we will tell now. One is known as static pressure. So what is a static pressure? Static pressure is the pressure which is there because of the intermolecular collisions. So that means if one is moving with the flow, then what is the pressure felt because of just moving with the flow is the static pressure. So this is the pressure experienced in moving with the flow. So this is the result of the intermolecular collisions, and this is the pressure that we fundamentally define. Now we are also going to define something called as stagnation pressure. So what is the stagnation pressure? Stagnation pressure is the pressure that is there at a point if the fluid is subjected to 0 velocity at that point in a reversible and adiabatic manner. So pressure at a point at which fluid is subjected to rest in a reversible and adiabatic. We will not go into the details of the reversible and adiabatic processes because these you will learn more in details in the thermodynamics course that you will have subsequently. But important understanding in our context is that one of the important requirements of this is it is a frictionless flow. So that means when the fluid is subjected to rest at a point, you have to make sure that it is subjected to rest in a frictionless manner. So whatever is the pressure that this tube is getting is the stagnation pressure. So this is also known as a stagnation tube because its reading gives an indication of the stagnation pressure, and this is known as a static tube. So you can, if you want to write the Bernoulli's equation between 2 points 1 and 2 which are located in such a close manner. So at point 1 if you have pressure as P, Ps or say P1 by rho plus V1 square by 2, we are not writing the Gz1 and Gz2, they are so close that the difference in height is negligible, is equal to P2 by rho plus V2 square by 2 plus Gz2, we are not writing again. So what is V2? V2 is 0 because it is a stagnation point. So the definition of the stagnation point is velocity is 0. So you can see that you can write P2 which is the stagnation pressure as P1 which is the static pressure, this is same as P1, this is P static plus half rho V1 square. That means stagnation pressure is a sort of property of the flow if you know the velocity of flow. But you have to keep in mind that this equation is derived by considering a frictionless condition, and frictionless condition is valid when you are subjecting the flow to rest in a reversible and adiabatic process. So the definition of the stagnation pressure is to be kept in mind. Stagnation pressure is not just pressure at a stagnation point. What is a stagnation point? The stagnation point is a point where you have 0 velocity, but it does not mean that pressure at that point is a stagnation point. Pressure at that point will be a stagnation pressure only if the flow is subjected to rest in a frictionless manner, because the stagnation pressure is defined in that way. It is not just sufficient, it is necessary that you must have the velocity to be 0 at that point so that the pressure measured is a stagnation pressure, but at the same time it is not velocity subjected to 0 in any way, but it is subjected to 0 in a frictionless way. The second important thing is, since these 2 points are very close to each other, and you can just say stagnation point, a stagnation pressure at a point just as a property which is dependent on the local velocity. So stagnation pressure need not always be measured through a stagnation point. So if you want to say find out stagnation pressure at a point, you can simply say that it is the static pressure which is the regular, the normal pressure plus half rho V square. That is the definition. So the stagnation pressure does not mean that you have to bring the fluid to rest at that point to get a pressure. It is like how you physically conceive that pressure, not that so it should not give you a false idea that whenever the velocity is non-zero, stagnation pressure is not defined. It is definitely defined. It is just a physical way of looking into its interpretation. Okay. Now the next we will discuss one or two important flow measuring devices, and the first device that we will discuss is known as a Venturi meter. So what is a Venturi meter? Say you have a pipeline and you are interested to measure flow through a pipeline. So what you are trying to do, say you have a pipeline like this, you want to measure what is the rate of flow through the pipe. So how will you do it? There are many ways in which it can be done it. One of the ways is by utilizing a device called as Venturi meter. So what is done? A part of the pipe is like replaced with a device. What is that device? The device is like this. So you have an accelerating section by having a converging cone, then you have a section of uniform a zone of uniform cross section, and then you again come back to the pipe dimension. So this is known as diffuser. This is known as a throat. And this is the converging section. Okay. So what is the objective? The objective is, see, by this way you are reducing the cross sectional area. So to maintain the continuity in a steady state, you are what you are doing. So if you consider now the points, let us say that you consider points 1 and 2. The point 1 was having the velocity as same as that of the velocity of flow in the pipe. Now at the point 2 the velocity will be more or less? It will be more, because the area of cross section has reduced. So since the velocity is more, now if you write the Bernoulli's equation, assume that it is a frictionless flow, then P by rho plus Gz, that term will be what? That term will be changing, and if we can find out a measure of that change, then it is possible to find out the velocity through the Bernoulli's equation. How we do that? Now let us say that you make a tapping of a manometer. That means, let us say that you consider a hole in the pipeline and a hole here, and connecting that with a manometer. Okay. So when you are connecting that with a manometer, see, we have not taken the point 1 at the inlet of the converging section, but at some location which is sufficiently away from that, because here the streamline curvature effect will tend to become more and more dominant. So you want to take it away from such a place where the streamlines are almost parallel to each other. So pressure at this point and maybe pressure at this point should not be very different because of the streamline curvature effect. So we are having a manometer in which we have a fluid. Now in which limb the fluid height will be more, or in which limb it will be less? Let us write the equation, the Bernoulli's equation along a streamline between the points, connecting the points 1 and 2. So let us say you have a streamline that connects 1 and 2. So you can write P1 by rho plus V1 square by 2 plus Gz1 is equal to P2 by rho plus V2 square by 2 plus Gz2. At the point 1, if you have this as the height of the limb, and at the point 2 if you have this as the height of the limb. Now I have drawn it in this way. Do you accept that it should be like this? Let us say a fluid, a mercury is there as a manometric fluid here, we call it rho m, the density of the mercury. Now is it an acceptable sketch? In this case the remaining is filled up with water. So if water is flowing through this tube, let us say this is filled with water, the same fluid with which it is flowing here. So is this acceptable? By this you are expecting that pressure at 1 is greater than pressure at 2. We will see that that may not be correct also, let us see, but this figure is correct. How that is possible, let us see. So let us write, let us say that this is the difference in height that we measure, say that is equal to delta H. So when you measure this height delta H, then from that delta H it is possible to write the equation of the manometric principle, that is you can write that if you have 2 points A and B at the same horizontal level, you have PA equal to PB. So when you write PA equal to PB, let us say that you are writing, say this is your reference for measuring Z1 and Z2 in the Bernoulli's equation. So this is your Z1 and this is your Z2. You can use any datum, but this is a convenient datum. So you can write P1 plus rho g Z1, that is equal to pressure at A, right, where rho is the density of the water that is flowing through the pipe, is equal to P2 plus rho g Z2 minus delta H plus rho m g delta H, okay, fine. So when you are finding out the difference in P1 and P2, P1 minus P2, you see that you can clean up the expression by noting that it is not just P1 minus P2 that is important, you have P1 plus rho g Z1 minus P2 plus rho g Z2, that is what is going to be important. So if you write P1 plus rho g Z1 minus P2 plus rho g Z2, then that is rho m minus rho into g into delta H, right. So in this figure you are expecting that delta H is positive, isn't it? This is just the dimension. Rho m, say this is mercury, so we know that it is much heavier than water, so rho m minus rho is positive, that means we are expecting this to be positive. So what this reading gives us? This reading gives us not the difference in P1 and P2, but the difference in sum of P1 plus rho g Z1 and P2 plus rho g Z2, right. So it is not giving us the pressure difference. So what it is giving us? So let us write this in a bit more explicit way. So we let us write it as P1 by rho g plus Z1. So we are dividing it by rho g. So P2 by rho g, because we know that in this process we will get something called as head, which we use as a terminology for this calculation. So this is rho m by rho minus 1 into delta H. This delta H is very important because this is what experimentally you can read, okay. So when you read experimentally delta H, you see that it is an indicator of not just the difference in pressure, but the difference in pressure head plus the elevation. So when it is flowing from 1 to 2, it is possible that P1 is less than P2, but P1 by rho g plus Z1 is greater than P2 by rho g plus Z2, okay. So this flow is taking place from a higher value of this collected term to a lower value of this collected term. This collected term, which is given by P by rho g plus Z, is known as a piezometric head. So P by rho g plus Z, this is called as a piezometric head. Why it is called as a piezometric head? The reason is that if you say have a pipe, and if you puncture the pipe or if you penetrate the pipe, say, and if you have a tube through which the water goes up, it is just like that static tube that we considered in this in the previous example. Then the elevation that it assumes here is the elevation because of its vertical location plus because of the pressure at static pressure at that point, and this tube is commonly known as a piezometer tube. So that is why the name piezometric head. So in the manometer, in this kind of an example, we do not measure the pressure difference, but we measure piezometric pressure or piezometric head difference. So in terms of head it is called as piezometric head. If you express in terms of pressure unit, it is called as piezometric pressure. So always keep in mind, in this case manometer is not measuring pressure difference, it is measuring piezometric pressure difference. These are very fundamental mistakes that people make. See, as I told in the very introductory class, that we are born with certain intuitions that it will flow from high pressure to low pressure, and you can clearly see that with a very simple example where it is not actually a practical example because we have considered frictionless flow, but even that it gives a very important insight that it need not be from a high pressure to low pressure. It is basically from a high piezometric pressure to a low piezometric pressure. Now fortunately what is important for this equation is only the piezometric pressure, because if you see, like if you write it in this form, you will get P1 by rho g plus V1 square by 2g, sorry, P1 by rho g plus Z1 minus P2 by rho g plus Z2, that is equal to V2 square minus V1 square by 2g. Okay. So this is something which is a very simple term for us now, because from the manometer we have got an explicit expression for that, that is rho m by rho minus 1 into delta H. So this we can write as rho m by rho minus 1 into delta H, and this is equal to, now you can express V2 and V1 in terms of the volume flow rate. So if Q is the volume flow rate, then you can write as Q equal to A1 V1 equal to A2 V2. Again, what are the assumptions? Rho is constant and it is a uniform velocity profile over the section, that is in viscid flow, viscous effects are not there. So you can write V1 as Q by A1 and V2 as Q by A2. So if you substitute that in this expression, it is possible to express V2 square minus V1 square as Q square by 2g into, no, this g is there, so no, because of division by g, V square becomes V square by 2g. So Q square by 2g into 1 by A2 square minus 1 by A1 square is equal to rho m by rho minus 1 into delta H. Okay. So from here you can solve for what is Q. Remember, it is very theoretical. Why it is theoretical? Because it has considered many idealizations which do not actually occur in practice. So we will keep this in mind, and in the next class we will try to identify that what are the idealizations which were here which need to be rectified, and what are the important design considerations that should go with this device matching with the non-idealizations. That we will discuss in the next class. But if it was ideal, just by getting the delta H reading you could get what is the flow rate through the pipe, because A1 and A2 you know are the areas of cross sections of 1 and 2 which are given geometrical parameters. So we stop here today, we will continue with that in the next class.